mills on fluidized bed reactors, advanced modelings, DEM, etc.
Okay. Thank you. Thank you, Kumar. I wish to thank the folks involved in putting this meeting together. I know it's also a lot of work. There's going to be a quiz on LS's talk after my talk. Anyway, today what I'd like to do is to talk about some work that I did with Professor Mike Dukovich and one of his PhD students, Eugene's son, at the Department of Energy, Environmental, and also Chemical Engineering at Washington University in St. Louis. You can see there from the title, it deals with the kinetic theory of granular flows and how it's associated with multiscale CFD modeling. Now, my first exposure to this area actually occurred when I worked at Monsanto, and we actually were developing a route to produce the chemical styrene using a fluid bed process that was somewhat like what LS was talking about, like chemical looping, in which we had two different beds, one in which the callus was being basically like reduced, and the other in which it was being oxidized. That was called the alternate route to monomer styrene ARMS, the ARMS project. That actually went up through the pilot scale, and then at that point it actually worked very well. But then Monsanto decided they wanted to be like a seed company, and anything involving chemical research started to dissipate. So today what I'd like to do is give a little background on why we want to do this work, discuss the Lorentz method and kinetic theory of gases, granular theory, and also Lagrangian method and how that impacts the RTD that we see in actual systems. Fluidized beds are one alternative reactor, obviously, for multi-phase reactors. There's a whole supermarket of course, multi-phase reactors that can be used. Some of the advantages of those reactors are shown here. Superior heat transfer, easier solids processing, lower energy costs, as well transport. Of course, one of the other important things is that we need to have a particle which is, of course, can withstand the attrition rate that can occur in a fluid bed. And there are special technologies that can be developed to harness the particles, and also to ensure that also there are pores at the same time so that reactants can diffuse in and out. If we look at some of the classical types of processes where fluid beds are used, in polyolefin, also combustion, typically we have Gilhart BED particles, and these are bubbling beds. In like turbulent fluidization, we have the classical acrylonitrile process. This is Ohio type of catalyst, bismuth-liptate catalyst, oxychlorination. The Fischer-Tropsch process, the blue process for that, phthalic anhydride, or roasting, fluid beds, dryers, and so forth. In fast type of fluidization, there's of course combustion processes and calcination. Dense suspension of reactors, catalytic cracking, flake anhydride is one process that has been shown to operate in that mode. Of course, today there's a lot of interest in catalytic fast type electrolysis, where we take biomass and we contact it with a gas in inert type of atmosphere. And that can be also done in like a fluidized bed. Okay, so of course we know in fluid beds, as in all multi-phase reactors, there's multiscale phenomena involved. We're starting on like a molecular scale. One of the critical aspects, of course, is to have a kinetic model. And in my experience, most industrial processes don't. Okay, there are kinetic models of empirical types, but typically understanding the phenomena on a molecular scale is often done in like empirical fashion. There's not too many processes out there that I know run where we have detailed kinetic models that can describe how reactants become transformed. Of course, then we go to the particle scale. Of course, in fluid beds, particles are somewhat smaller, obviously, than a typical fixed bed. So those phenomena are shown there on that scale. Then, of course, we have the phenomena occurring on like local scale. So scales that bubbles in a fluid bed. Here we see how the particles, of course, can be contacted by the gas, or they may not be contacted by the gas, which results in gas bypassing. And of course, all this phenomena go together then on the reactor scale, where we have to worry about things like flow patterns of the gas and solids, and all the other types of transport processes that, of course, can occur. So you see here that we're trying to obviously connect scales on the order of that span from 10 to the 9th, 10 to the 10th or so. So it's a very large range of scales that have to be, of course, connected. Of course, one of the more fundamental things to really understand in any process are the reaction kinetics. And again, as I mentioned earlier, many times in practical processes, not a lot of knowledge is known about those on the level that we'd like to have. So there have been a number of examples in the past when fluid beds have been scaled and they have not been successful. Okay? And why does that happen? Okay? One thing I could say is that when it does work, you'll hear about it. When it doesn't work, you won't hear anything. Okay? There'll be a lot of silence. Okay? So, but oftentimes in many practical processes, scale up is based upon experience. They start at a lab scale. For example, when DuPont worked on the process for developing butane from like anhydride, that work started in small fixed beds to test catalysts. Then it went to a quarter-inch riser reactor. Then it went to a 5/8" riser. Then it went to this pilot plant reactor that was in Ponca City, about an 80-foot tall riser reactor, before it went to the commercial plant. So it went through about 4 different stages until it was actually operated on a 100 million pound commercial plant. Well, we obviously need to know reaction kinetics and, of course, all the information which is related to that, reactor models with proper phenomenological models to describe how these systems operate. First, over the years, many different approaches have been used, and we want to take a look at the use of multiphysics and how CFD can be used to do that. Okay, so when we characterize then multi-phase reactors, we typically do it on the scales as shown here. On first the macro scale, we have the reactor itself. Then we could go to the mesoscale, where it was Olarian, two fluid types of models. Or we could go to the Olarian, Lagrangian type of model, in which we couple the gas flow with the mechanics of solids on the solid level. So there's different approaches, of course, that can be used. Typically, when one is working in practical processes, because of time management is beating on you, where the results when we go to commercialize, because time means money, we oftentimes have to use simplified types of approaches. And only after when a process is up and running, is there time to go back and look at such things on the detail that we'd like to hear. So therefore, like a key thing is to be able to do these things quickly and to be able to have experimental validation of what happens. So one of the well-known methods is the Olarian method, and it's related to the kinetic theory of granular flows. So we know the solids momentum equation is shown here in the two-fluid model. Of course, the key terms here that we need to use closure laws for here are the solid stress and the solids pressure terms here at the end. So we need a closure law, and that closure law needs to, of course, relate physical properties of the fluid back to the hydrodynamic parameters as well. So we need to come up with some way of doing this. So what's been done, of course, we know from the kinetic theory of granular flows, adopted from the kinetic theory of gases, of course, is that we start out with a velocity distribution function, F, which is a function of some vector coordinate r, c velocities at time t. We know that in a differential space, that relates to a distribution between some c and delta c and some r and r plus delta r. So the ensemble average particles are shown by n, integration of that velocity distribution. And say any quantity, then psi can then be obtained by integration of that quantity over that velocity distribution. So then that leads, of course, to our generic transport equation of the mean, which looks like the form that we see here below, in which you have a source term here that, of course, kind of defines the rate of increase of collisions, if you will, in that particular system. Okay, so that then will lead to collisional so-called flux and source terms, which have the forms here. We're going to go through all different terms, but then we have a pair distribution function. And the first type of approximation that we typically use is to describe F in Maxwellian type or Gaussian distribution actually, which then will lead to a gradient, the log of those distribution functions as shown here in that particular equation. All right, so the classical approach is used to get a small model, shown here, which assumes, of course, that only the normal dissipation, which is defined like restitution coefficient. That restitution coefficient is defined as a ratio of light velocities. I kind of think of it, if you ever played billiards, like billiards or pool, you have a cue ball, the cue ball hits another ball. So basically, you're taking the ratio of the velocity of the velocity that occurs after the collision to that occurs prior to the collision. We call that, of course, the restitution E. Now, in his model, he basically only accounted for the normal type of dissipation. Here, what we're going to do is we're going to look what happens when we account for the tangential dissipation of kinetic energy. So we could define then define this parameter, just like this, we call it the tangential parameter, and this, of course, can be defined as a ratio of the two quantities shown here. So you notice here that basically you're subtracting off, of course, the velocity is associated with a normal type of dissipation. So the impulse function J can then be defined as here as the difference between the initial and the final velocities. Okay, as shown here. Jm is proportional to the difference in those velocities. So what happens then when you account for the tangential dissipation, you actually end up with this term over here. So in the original Geddes-Fowles model, you have this term, but if you account for the tangential type of dissipation, then you end up with this term which is shown here. That then can be combined to give this type of expression shown here. Okay, so then if we take the parameter psi to be momentum, m times c, then of course we can then look at the difference between that particular, look at that parameter after and before the collision, which we get this type of equation. We can also do the same for energy, which is shown here. So then that will then lead to these expressions, which now, of course, contain different terms than the ones in the original formulation you get us about. Now we need to do that derivation in spherical coordinates, everybody's favorite coordinate system. Okay. So what we'll do then is we take this and we're going to then perform the various integrations of this in spherical coordinates, and we're going to see what we end up with in terms of the final expressions. Now, the math operations in doing this gets quite complicated. We first did some of these manually. Okay. This is not all the steps, just some of the steps. We then went to a symbolic engine, Maple, developed here at the University of Waterloo, and we developed the mathematical tools to perform these various types of operations. So it takes multiple pages. Those of you that knew Professor Harris, he would say, suppressing the details which are painful, he would show them the final result. Okay? But here, of course, this is one example. The other details are given in some of our previous documentation. Now, what is it that you find after this exercise? Well, here's our momentum stress tensor, pressure, like Geddes-Fowles, here's expressions over here. When you include the tangential contribution, you get some additional terms. So here we show the different components of the pressure, the normal, and the shear stress terms right here. Now, what's very interesting about this, as you might expect, that the pressure term, which is pressure only, of course, works on normal to a surface. These two terms here, of course, are the same, but the others are not. And what's interesting here, if you set the tangential restitution coefficient equal to 1, then you basically find out that you end up with the exact same expressions that he was able to develop. So that basically told us that our math was correct, and also that physically that results made sense. So when you go down a little further, so here's the terms, and here's the conductivity K expression over here. And you can't see that, but it's all there. And the energy dissipation rate is shown down here. And what you find out that if you use about the same value for the for the tangential restitution coefficient as you do for the normal one, you find out that the dissipation rate is roughly a factor of 2 higher, okay, than it is in the case of the good spot model. Okay, so a lot of things had to happen in order to end up with those final equations, but those are the final results. Of course, what is it we're trying to do here? Well, we're trying to basically advance our knowledge in terms of how to formulate these types of models, okay? So you can say, well, 2 like billiard balls, how can that describe a fluid bed? Well, I think that tells us something about what we have to do in the future in order to develop better models, right? Okay, now, okay, well, let's take a look here. Here's an experiment involving cool-lead flow of particles in which the normal stress and the shear stresses are basically compared. Here we show the results that were obtained from this work, which is the solid line. These are the normal stress prediction as a function of the solids holdup, and the same over here for the shear stress. And you can see by including the tangential factor that you get a better agreement, at least over the range at which data was obtained, than you do if you just include the normal force. So we felt that result was very promising, and it basically provided encouragement that what we did was indeed correct and moving in the right direction. Okay, now what we're going to do is we want to take this result and put it into a CFD simulation for a fluid bed. For that, we use open foam. Mentioned here, of course, several times today. We like it because it's an open source. One can use some of the subroutines that have already been developed, but also one can go in there and write subroutines or functions that can capture the physics that you have developed. So this shows the results of an open foam simulation on a small fluid bed, 2D fluid bed, 0.28 by 1 meter in diameter, with the official gas velocity shown here, a restitution coefficient, get a spot model of 0.8, and a tangential distribution coefficient of like 0.5. So there's actually like a simulation here. I guess it's not going to work for us, but in the case. Okay, so what happens then? The reason why we picked that one because this is a system where data is like available from the solids volume fraction as a function of distance, or axial, or as a regional coordinate. So what you see here is the solids volume fraction. Here's the experimental data, and this would be the dashed red line is the solids volume fraction that would be predicted if you get a spot model, and the green line there is the one that we predicted from this work. So you see, it does give you a slight improvement than what you have from the get a spot model for the data. So it's a step we believe in like the right direction. Okay, now what we want to do is to use this and look at the Lagrangian method in resonance time distributions. Obviously, in a chemical reactor, the important thing obviously is that the solids contact the reactant gas. Of course, one of the things that's used to characterize solids is to perform resonance time distribution experiments. So in like a conventional type of tracer method, one would introduce a solid tracer someplace over here in, say, in the riser section. Then one would then monitor the behavior of that particle or the concentration of the particle as it exits the system. So here we might see a typical solids RTD curve. In this case, this is actually that's collected with a photoluminescence type of tracer. So now what we can do is we're going to perform an experiment using the computer augmented radioactive particle tracking system at Washington University. This is done in a riser type reactor in a closed flow system. So what was done here is that a radioactive particle is introduced at point A. There's a radioactive detector located here and another radioactive detector at the top. Over here you see the output from those detectors. Okay, it's a little difficult to see here in the light. So you have the detector at the bottom, there's one at the top over here. So you see every time the particle passes that plane, it will be detected by this particular detector. So a particle is introduced at A, and then leaves the system at B, right here. It enters back into the system then at C, and then it finally exits over here at D. So you see here these points, A, B, C, and D. Well, the time that the particle spends outside of the closed system really does not count toward the true RTD. One needs to basically, the time that is spent in the system is really between A and B, and like C and D. C and D, of course, is the what we call the first passage time distribution. This is the actual time that the particle spent in this region right here during its first passage through the system. Now, if one was doing this with a conventional tracer type of approach, you would then basically measure, you would think that the RTD was based on the time that the particle spent between points A and D. The fact is, that's not correct. It's actually the time that is spent between A and B, and also C and D. Okay? So what this does then, this gives us experimental data that we could then use in conjunction with a CFD model to see how we could basically track the particle residence time. So this shows solids RTD measured from CARP, and it shows how under two types of conditions, a fast fluidization regime and like a fluid regime, and it shows how the fit between an axial dispersion model, which is shown here in like the solid lines, okay, in each case. These are actually all the points that actually come from CARP. So you see there that the axial dispersion model really does not provide a very good fit between the data and the model. Now we could use the Eulerian, of course, Lagrangian method, you're all familiar with, where we have the random balances for the gas phase. We have the solids tracking part of it. So X is the local, of course, position. And then we have, of course, the various forces acting on the particle, shown here. The last one being the collision. And this is where we're going to use the updated model that accounts for the tangential, of course the dissipation. So we go to OpenFOAM, and we write the code in Lagrangian variables. And what we're able to do then in OpenFOAM is we basically can track the particles. We can define what is the exact residence time that's in the riser. We could compute what we call the improper residence time, it was as detected from a conventional tracer experiment. We could then find the first passage time. We could find the trajectory length, how long it actually traveled. And then if we go with kind of a conventional compartmental model, say a core annular model, we could actually compute how long that particle spent in the core and the annular region, and a number of passing zones, and from that we could actually compute the interchange flux of the particle from one zone to the next. So this shows a schematic of the CFD trajectory. This is using like 1,000 particles or so in the simulation. So this is the blue particle, which is the fresh particle that was introduced into the downer. Then it goes over here into this zone, which is not out of that zone, so we're able to mark it. So we want to record when it's in the proper zone and when it's not. Okay, so we want to keep track if it comes back out over there. We don't want to record that as a true passage time. It then goes back into the system, so we want to count that as a proper passage time. It can go up the riser, it's still in, so we want to count that. Now it's out of the riser. Now it goes back in, so we can start counting again. And then it's back out again. So we want to then build it, we can then keep track of where all these particles are, so that gives us a way of marking what is the true RTD in each of those sections. Okay, so we're going to record that as we do the simulation. Okay, so here's our test riser of 1 centimeter in diameter, 10 centimeters in height. We put in 1,000 particles, and we perform the simulation using OpenFOAM. And we keep track of where all those particles are in this bigger system. So here we have an animation. Let's see if it works. Okay. Okay. So, okay, it doesn't work here for some reason. But in either case, what we're able to do then, we basically put the particles in here. This is our initial condition. Particles start moving through the system, and we're able then to keep track of how many particles enter and leave the system over that time, and then from that we could then compute the different passage times. So what we see here is a comparison of the RTD that you get from Lagrangian particle tracking versus the one that you get from the conventional tracer method, keeping track of where those particles are. So if you look over here, you see that the conventional tracer method says that the mean of that curve is 0.27 seconds, whereas, as you would expect, this is able to account for the time that particles spend Outside that section, it's a few hundred seconds less. And of course, the standard deviation of that curve is smaller, meaning it's more, of course, plug flow type of behavior versus what you would get from a conventional tracer type of test. Now, if you try to fit those data to axial dispersion or like tungsten series model, you do not get, it's very difficult to get very accurate fits with those single parameter types of models. Now we can now look at the first passage type distribution, which is the amount of time the particle spins in between those planes C and D, okay, without going in and out of the system. From the conventional tracer method, here's our mean and our standard deviation. The first passage time we see is about a tenth of a second less, and it has about factor 2 less standard deviation. Means, of course, it's approaching more plug flow type of behavior. Now we can look at the trajectory length distribution. We can define the macro mixing index. It's actually a ratio of the mean trajectory length over the axial one. In the case of pure plug flow, that ratio should be 1. We see in this case it's slightly greater than 1 because of a little bit of back mixing which is occurring in the system. So we're able to obtain that particular parameter in the system. Now we can keep track of how much time the particles are spending in the core and the annulus. So therefore we're able then to compute and look at the RGDs in those two zones. So here we see how the RGD behaves in the core. Here's the mean of a 0.12 seconds versus over in the annular region about a factor 2 greater. Whereas the standard deviation, of course, is smaller as well compared to that in the annulus. So we know that this physically makes sense because we know that as the solids are carried upward in like the core region, the solids exchange with the solids in the wall that are tumbling down on the core, and there's exchange occurs, and that, of course, adds to the back mixing of the system, and of course, affects the mean residence time because particles are spending more time in the system. Now what we're able to do is we're able to also compute the interchange coefficient. We know that the number of particles that go from the core to the annulus and the annulus to the core, they should be balanced because obviously because of it's a non-reactive tracer. And so we see that when we do that, we're only off here on about 12,000 particles. We only missed the number by 7. So it shows that the simulation is accurate and we're able to balance it. So that then allows us to compute a particle exchange coefficient, which we can derive there from those types of simulations. Okay, so what I've tried to do today is to give you a little overview of some efforts toward kind of advancing our knowledge in the kinetic theory of granular flows. Of course, we know that design and scale of fluid beds is very challenging and it continues to be a challenge. And I think as Ellis was showing in his work, okay, those are new types of technologies, and having appropriate scale-up methods is very important. We also know, as we look at conversion of other types of feedstocks involving solids, biomass, maybe hybrid systems, for example, being able to apply these techniques to understand how to scale and to optimize the selectivity to the desired products is very important parameter. Modeling is very important, obviously, to link experiments, because we saw, for example, the use of the CARP experiment provided a very nice way of verifying how the Lagrangian or Eulerian type of simulation worked, and how well it was able to capture the physics of the particle moving. Now, in order to, of course, develop closure laws, we need to work on the physics of how particles interact. Okay? Now, in the model that I showed you, I didn't account, for example, for torque and also dissipation energy. So the next level there would be to deal with how does energy basically dissipate because the particle is spinning, and one would have to do, obviously, a torque balance in that case, a balance of angular type of momentum. Okay, that would increase the complexity significantly. That's really what's necessary to take it then, of course, to the next level. Now, we see here that when we use these models over here, and we basically can use particle scale physics in order to understand how such things work. Now, in our case, we just added the tangential type of equation, okay? Even that alone took significant effort in order to derive those particular equations. So if we want to go to other more complex type of cases, distribution of particle sizes, and other types of interactions, and of course that would increase the complexity, but it would also increase the basically the accuracy with which we can predict how such systems operate. Okay, so we also show there by using particle tracking how we're able to predict and show how the interchange and so forth work. Okay, so that brings my discussion to an end, and be glad to answer any questions you may have.
We have a lot of time for questions and discussions.
So, clarification. So in your CFD simulations, you're using 1,000 parcels, kind of lost in.
I'm sorry?
In your CFD simulations, you're using like 1,000 parcels.
Yes, well, using 1,000 particles.
Particles.
Particles, yes. So they're put in the bed at time t equals 0, and then we keep track right here. Is this what you're referring to?
Yeah, is this particles only to track the statistics, or is it actually you're doing a two-fluid simulation?
Yeah, well, it's actually a Eulerian, like Lagrangian type simulation. Let's see what it's like here. Okay. So what we're doing, we're using Eulerian equations along with solid phase equations. But here, what we're using the collision model that I showed that we derived. Okay. Okay. So then we're keeping track where those particles are going when they travel in the system. Okay.
1,000 particles, it will be so dilute. So.
Well, our computer was not a huge supercomputer. Okay. So you're welcome to take 10,000 or 100,000. But you can see though, it gave the correct results in terms of satisfying the mass balance. For example, over here. If you look at the end over here, if we look at our ability to keep track, okay, we're able to keep track of the fact that the particles exchange between the coordinate region and back, in fact, this is balanced. So the computation is going to be correct. Okay. If you want additional, you want to go to a larger scale system with more particles, it's just a matter of using the same approach, but just increasing the number of meshes and the scale.
So, just a basic question, with 1,000 particles, only you expect to get the kind of clusters between 3 to 4 angles?
So here's our density, 1,000 particles, a tenth of a millimeter, 2,000 kilograms per meter cube. Okay, and here's our Reynolds number. So it would exhibit coordinate behavior under those types of conditions. Yes.
A question about the ergodic equivalence of a single particle approximation of the RTE versus the conventional RTE, where you have a cloud of particles that are traveling with about the same history. So it's like you have a wave of these particles that are heading to the sensor, and you're getting this picture.
Right. Now, are you saying in that case when you do the injection, you inject more than one particle?
Yeah, for the classical.
Okay.
Then when you try to get either the trajectory length distribution or its time equivalent from a single particle, then it seems to me that part of the divergence would also originate from the very long-term observation in the Karp experiment of all the possibilities your tracer is going to undergo.
Right.
So I'm just wondering if by running a test for, say, 24 hours, and then chopping the observations, so taking packets every 6 hours, and see what is the sensitivity
Yes.
of that RDE that is gathered from one single particle to the one that is being obtained from a cloud of particles.
Yes. Yeah. I think that's a very good question. It's a matter of basically having more sensors, more data collection capability. But I think that's definitely a very good point. I think it's something that should be really considered in the future, because whenever you're doing averaging, right, you're looking at, like mean residence times order of like tenths of a second, right, and you're averaging over 1 or 2 orders of magnitude greater, then you're getting some type of pseudo average. And the question is, how far is that pseudo average deviating from the actual, right? But if we did have, more sensors, higher speed, data collection, then I think you're correct, we get a more true picture of what's actually happening in that system. When you get a giant $100 million grant, we'll go under your act, we'll try to do that. But that's a very good question.
Frederick, this might be a very naive question because I don't understand mixing and all these things very well. What is your trajectory length, which is kind of a linear measure of how particle traverses this domain?
It's basically
Versus-
it's basically how far it's traveled during this passage time.
So what do you call well mixed or mixed?
I'm sorry?
Where, like mixing in this one would be more like the configuration of many particles that are dispersed over here, or what do you call well mixed?
Well, your trajectory length is the time that the particle spends between these two planes, okay? Or the length that is traveled, right?
That's mixed.
That's your trajectory length. That's your total trajectory length.
So if it just spun around there, like helical path.
Right. Well, you see here, this is how during this time how the particle behaved. It eventually made its way out, but it obviously was not flowing like we often think and say quasi plug flow or actually dispersed flow. Okay. So this is a trajectory length. Wherever that length is, how long it traveled. Okay. If I'm driving from here to Calgary, maybe I take some detours and I drive around some mountains. That's my total length. Okay. That's my trajectory length.
And that would directly be related to some macro mixing. It has nothing to do with multiple particle configurations, such as how well spread they are inside this horizon.
No, it doesn't.
Okay,
It's just a single particle. I think it gets back to what fossil is asking really. What happens when you put multiple particles in there, and how would they behave? How would multiple particles behave if you could say distinguish between, say you put in 10 different particles, and you could track each of those like separately. If you had some way of like detecting those, how would they behave, and how would that averaging behave depending on the averaging time that you're taking, right? I think those are all good questions, but those are unanswered questions.
Okay, all right.
If not, I guess let's take a coffee break and come back at 4. What I would like to do is set it up for a panel discussion on today's talk. Looking at technology development versus the status
And from there, we're just going to engage people Let me know you want to proceed. Let's just material to help. Okay.
So are we in agreement?
So apparently Kumar wants to summarize first.
Okay.
Yeah, I just wanted to summarize one thing. I really met you. If I did what I did some years back,
After listening to you today.
I knew my technology development. He was an IIT as a grad student.
Okay. Where are you at now?
I am at the University of Florida.
Oh, okay. Yeah.
So I will pose the question.
Were you in
Yes, I was a graduate student and I was graduating.
Oh,
Just to give inspiration to people to pick up something.
That's right, and I joined in 1971 and I did a master's with Einstein. He did his PhD with Einstein.
Right.
And I did my PhD with Prentice.
Here we're waiting for
Don't do it. Things I will. I can I had a gas. That's a good IGT.
Okay.
And Mike actually taught me reactors.
Okay, did he? Okay.
Because I never had an undergraduate, of all things, an undergraduate course in reactors.
Okay, right.
Shocked.
Yeah, I taught that class.
And he was an excellent teacher.
Yes.
So you did your PhD also
Yes,
there
yes.
with him?
Yes, I did.
And then you were there for some years after
Well,
that?
I was in Marshall University, and then when I graduated, I went to work. Yeah, I went to Montana, and then I was there for almost 10 years. And then I went to work at DuPont.
And Wilmington?
Yes, I was on experiments.
Did you run into Jim Trainum? Was he
Oh,
there?
yes.
Okay.
Actually, he was a director. I was in the engineering lab for a while, and he was a director.
Okay, I'm a technical consultant for a company called Chevy Flow that does works on spectral filters.
Oh, okay.
And it's very, very what people use the word high fidelity. I always wonder what is low fidelity. The thing is, the very it's extremely accurate. So we're actually consulting with him.
Oh, okay.
He's now in Boston.
Okay, I know he was.
He retired from.
He retired. Well,
Then he went to PPG.
right, and then he worked. Then he went to. RG Research down Research Triangle Park. Right?
I didn't know that part.
Yeah.
I want to try this out. Anyone.
Yeah. He went there.
If I try this, then I'll take this away, so I don't get these things mixed up.
Are you on the panel? Oh, okay.
I will be helping still.
So you can,
Yeah.
Okay.
that's what I
No, you need somebody to
The
constantly ask.
enforcer. The dirty Harry. You'll be the dirty Harry of the.
Okay, now what do I do here? Microsoft is trying to use the code.